So chapter 8 is Introduction to Calculus. This class is called Pre-Calculus. Yeah, and so all the time up to now has been the pre part. Now we're getting to the calculus part. So what is calculus? Anyone have an idea what calculus is? Some people claim it's a 4-letter word, as it says right here, but it's not a 4-letter word. It's an 8-letter word. Are there? C-A-L. Oh, okay. All right. Right. Nice. Okay. So calculus, has anyone ever heard of like someone had to go to the hospital because they had a calculus? Yes? Yeah, calculus comes from the root calc, like calcium, right? Which means stone. Calculus comes from the root word for stone. So words like calcium, calculate, not California, by the way, as it says right there. They all come from the root word that means stone or pebble. So why do you think they would use that root to describe the capstone math course in high school? Because it makes you want to smash your head with a rock. Right. And then you would go to the hospital for calculus. Yes. All right. It all came full circle. Beautiful. We kind of talked back in the beginning of the year when we talked about the number systems, right? Cavemen walked around and they were like, ooh, rock, right? And they picked up rock. And then they found another rock. So they're like, ooh, rock. And after a while, they were rock. So they needed a way to count their rocks. So then natural numbers came up. 1 rock, 2 rock, 3 rock. And then other cavemen got jealous. So then the idea of 0 came along. We have 0 rock. And then they had too many rock in their hand. And then they fell and broke. And so we had fractions, right? But they used rocks to count with. All right. And so that's why we use calculus, kind of the most primitive way to count with rocks. We use it now as the root for the capstone course in high school. So here's a little meme that I made. Is that a meme? I don't know. It's not like the meme. It's like before memes. This was like a pre-meme, right? So like a T-Rex right there needs 2 pebbles to keep track of how many arms he's unable to use. Okay? Right. And he wouldn't be able to even smash them together. So if someone asks you what is calculus, like the math subject, you could answer it like this and be correct. So without looking, you can look. What is, in a nutshell, the study of calculus? What is calculus? It's the study of change, right? Like nickels, dimes, quarters, penny, right? So like if the cash register doesn't work and you have to make change on your own, that's what calculus is about. How do you break a 5? The bill's $1.36, someone pays with a 5, you're like, oh crap, I got to give them money back. That's calculus, right? The study of change. Actually, not the study of change like coins, but the study of things that change, right? Like evolution. Yeah, evolution is also the study of change, right? Calculus is very similar because calculus itself has evolved from the guys on the wall here. They've all contributed in some respect. The guy on the far right, Archimedes, is the father of what's called integral calculus. And then Newton, the guy right next to him, and Leibniz over here are the fathers of what we call differential calculus. Okay. So yeah, what in this world changes? Anything? Anything change? Us. We change. How do we change?
Hopefully good.
Hopefully for the better. Okay. Do we change at a constant rate or at a variable rate? Oh, probably a variable rate, right? Probably at a variable rate. Is there anything else in this world that changes at a variable rate? Nope, just us. We're the only, just us. So calculus is the study of people and how they change. How about the temperatures outside? Are the temperatures outside changing? Ooh, kind of warm now. Yeah. Do you think they change at a constant rate? No, they change at a variable rate. If things change at a constant rate, you don't need calculus to study them. But most things change at a variable rate. And if anything changes at a variable rate, you need calculus to study it. Okay? So that's what calculus is in a nutshell. It's the study of change. Okay. So mathematically, we're going to start with the simplest type of polynomial, lines. What type of lines? Straight lines. Right? As opposed to curvy lines. Right? Connor's like rocking out like a headbanger. Sweet. Okay. So you may not know where this is going yet, but I'll take you there, all right? So let's just review some Algebra 1 stuff, right? Algebra 1 was the study of lines because it was x to the first equations. Algebra 2 was the study of quadratics, x squared. If you were to take Algebra 10, it would be the study of 10th degree polynomials, right? Maybe not. All right, let's go ahead and then find the slope at any and every point along the line passing through these 2 points. Okay, so first of all, let's plot the points. -2, see, this is real basic. -2, 3, there's a dot. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There's the other dot. So if I connect those dots with a straight line, and we could do the snap to feature here. There it is. What can you tell me about that line besides it's red? It's straight. Very good. It's a straight red line. What else can you tell me about it? Yeah, it's probably a good time to log in to your Notability and turn your game off. There you go. Okay. It's increasing. Very good. This line is increasing. It's increasing. How do you know it's not decreasing? If I was to jump on right here, I would roll down to the left. That would be decreasing. Why do you say it's increasing? Because what? Because we always read a graph like we read a book, not like a Japanimation book, but regular books. From left to right, yeah? We read graphs in chronological order, in increasing order from left to right. So from left to right, this is increasing. Good. How is it increasing? At a constant rate. Good. This is increasing at a constant rate. Can we figure out the rate of increase? We absolutely can. What do we call that? The slope. Good. The slope in Algebra 1, you probably just learned it as rise over run. And you went around saying rise over run all the time. Rise over run. And then you realize that you can actually rise by falling, right? Because the rise is not always up. You could actually fall. Like when I get out of bed in the morning, first thing I do before I rise is I fall. I fall to the ground, and then I rise. Okay? Just gravity working when you're my age. Okay? So you can actually fall and then run left or right. And you knew that you could probably find it by doing y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? Remember that? And then there's like, what are those little subscript numbers, right? And they're called subscripts. You had to ask what the subscripts are. You knew what they were. And then maybe you substituted the Greek letter delta and put delta y over delta x. Delta here not meaning rich, fertile crescent, but change, right? Change. The change in y over the change in x. So that's what a slope is. It is the rate of change of some quantity with respect to another quantity. That's what a slope is. A slope is a rate of change of one quantity with respect to another quantity. So whatever we're measuring on the y-axis changes with respect to whatever we're measuring on the x-axis. Now, without any applications, you're just measuring how y values change with respect to x. But it becomes very powerful if we were like sketching temperature in degrees Fahrenheit against time in hours. Now the slope would tell you how fast the temperature is changing with respect to time. That's pretty powerful, okay? So maybe your Algebra 1 teacher didn't do a really good job of giving you the application of slope. Slope is the slope this we're going to find is the average rate of change, the average rate of change between 2 points. That's what it is in general. So that's the application. So if you have like 1 point x sub 1, y sub 1, and another point x sub 2, y sub 2, and you want to know how a quantity changes between those 2 points, you could find the slope. All right, now for a line, what do you know about the slope at any point compared to the slope between any 2 points? As we already said, the slope is, or the function is increasing at a constant rate. So the slope, is the same anywhere and everywhere. Anywhere and everywhere. Which is why we use lines to help us begin to understand change that isn't constant, okay? So let's go ahead and find the slope of this line. We have our 2 points, so we'll write it like this. We'll say slope. What letter did we use for slope? Back in Algebra 1. What's the word under slope? Average rate of change between 2. Rise over run? Increasing at a constant rate. Slope is the same anywhere and everywhere. Sorry, my handwriting's horrible. Slope is the same anywhere and everywhere. No, it was from y equals what x plus b. Ah, there you go, mx plus b. Where m was the slope and b was the y-intercept. So m we used for slope. Ym, s was already taken for distance. Ys for distance, long story. Right? So ym for slope? M for math. Good. Yeah. Slope means kind of pitched, right? Steepness. So 1952, Sir Edmund Hillary and Tenzing Norgay. Mount Everest. Yeah, mount. Right. Mountain. Mountain. We climb mountains. Mountains have slope, right? Mountains have slope. And so M is not for mountain, but it's kind of related. It's from the French verb to climb, which is, any French in here? Anyone speak French? What? Croissant. Yeah. It's monter, I don't know. One's Spanish, one's French. They're cognates, really. But it's the French verb to climb. To climb. Yeah. To mount things. Right? The B is y-intercept. Well, we use A for x-intercept and B for y-intercept. So since x comes before y in the alphabet, A comes before B in the alphabet. So there's no, great story for that. Right? No great story. Some things don't have great stories. It's just a sequence in the algebra. But good question. All right? So we'll go ahead and find the slope here. It's the change in y over the change in x. So that's going to be a 6 minus 3 all over 5 minus negative 2. Now, you can actually do it the other way around. You could do 3 minus 5 over or 3 minus 6 over negative 2 minus 5. But you want to get in the habit of doing right minus left, okay, on your x's, because x is your independent variable. So if you do the x value that comes on the right minus the x value that comes on the left, those go in the denominator. This right here is very important, which is the same thing that this is right here. We call that the DQ. And now you're hungry for a hunger buster. It's fan food, right? In this case, DQ stands for difference quotient. I don't know. Like in Connecticut, do you buy the Dodge Ram Texas edition? Or do they have the Connecticut edition, right? Tiny little wheels. I don't know. It's called the difference quotient. What does DQ stand for? Difference quotient, right? And it gives you the average rate of change. The average rate of change. We've already said that. Okay, so let's compute that. That is 3 over 7. So that's the slope. So that's not only the slope or the average rate of change between those 2 points because it's a line, it's the slope at any single point, right? Now, if I was looking for the slope at a single point, that's a little bit different, okay? Let's write that right here. The slope at a single point, does that even make sense? How can you find the slope at a single point? Well, your slope equation requires 2 points, right? To find the difference between them. So how can you find the slope at a single point? Well, for a line, it's easy because the slope between any 2 points is the same as the slope at every point. Well, if the slope between 2 points is the average rate of change, the slope at a single point is what we call the instantaneous rate of change instead of the average rate of change. And that's what the police officers after school in Kentucky are very, very interested in as you drive home. They're interested in your instantaneous rate of change. They clock you with a radar gun, and they're saying, I wonder at this given moment how fast their position is changing with respect to time. Right? And if that exceeds 20 miles for every hour, right, they usually give you a lesson. It's like, here's a ticket for admission into a class on why you shouldn't speed. And like, oh, where does the class meet? And they're like, it doesn't meet. This is your lesson. Just pay the fine. And they're like, I don't get it. And he's like, have a good day. Okay? No. No, that's a warning to y'all. That's a warning to y'all. Be careful, right? Because it's embarrassing to get pulled over and then all your friends pass by going slowly like, ooh, look, it's so-and-so, right? Yeah. But the instantaneous rate of change is different than the average rate of change, because we want to know in general how fast is something changing at a single moment. That's what we're really interested in. And we can't use algebra for that, because algebra requires how many points to find slope? 2. So if we're interested in finding slope at a single point, we can't do it using algebra. We need something different called calculus, right? So here's where we're going. So there's the slope at every point and the slope at any point. So for a line, again, because it's so simple, we know that 3/7 is not just the rate of change between 2 points, but it's the instantaneous rate of change at any given point, right? It's very boring. It's like driving on cruise control. 3/7 miles per hour the whole time. 3/7 miles per hour the whole time. 3/7 miles per hour the whole time, right? Now that might also get you a ticket on Kentucky, right? Because that's just too darn slow. 3/7 mile an hour, right? Sometimes they do have minimum speeds. You have maximum speeds, and then there are minimum speeds. Because if you drive too slowly, you're an equal hazard. Okay. All right. So let me kind of, before we move on to the next one, let me just kind of inform where we're going with this. Let's say I had the graph of x squared, and I want to know how fast this graph is changing right there. Let's say at x equals 2. Or let's do 3. Let's call that 3. I want to know the slope at that point. What does that mean, the slope at that point? Well, is that a line? You could say it's a curvy line, but we don't really call that a curvy line. We call it a curve, right? We actually call lines curves. We call them straight curves, which are very hard to hit in baseball. Okay? As you'll see, George Springer went 6 for 6 last night. That's more rare than hitting for the cycle. So anyway, so I want to know how fast is this graph changing right there at that point. I want to know that. I want to know at that moment how fast it's moving up vertically with respect to how fast it's moving horizontally. Now we're getting into component vectors from physics, right? Okay? We have something that's moving along a curved path, but it's got some components moving up and to the right as we go from left to right. But I want to know how fast that graph is changing at that moment. Well, that's the same as asking you for the slope at that point. So we have the point 0.39, yeah? And so we pull out our algebra formula, and it's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And we want to calculate the slope, but we only have 1 point, and we need 2 points. So what's the problem? We need another point, right? Now, if I chose another point like 0, 0, I can then draw a line connecting those two. We like to use lines because they're real easy. But if I calculated the slope of that green line, would that give me the instantaneous rate of change of that function at 3? No, it would give me the average rate of change between x equals 0 and x equals 3. Okay, and we call that, again, the average rate of change, which would be called the secant line. A line that connects a curve in 2 points is called a secant line. Yeah, we're reusing the terminology from the trig. It's a secant line, all right? So that's only the average rate of change. That doesn't help us with our interest in wanting to know how fast it's changing at that single point. So what we really are interested in, if you were to draw this line right there, I'll use beefy brown, that comes in right here and kisses the graph, glances off it right there at 3.9, okay? It's like surfing the curve with like a surfboard from underneath. That line we call the what line? Do you remember that from geometry? That's the tangent line, yeah. And again, we're reusing the terminology from trig, right? It turns out that we want to find the slope of the tangent line. If we are interested in finding how fast the parabola is changing at that single point, 3, 9, we are interested in finding the slope of that tangent line. So what's the problem? Well, we have the point 3, 9. Do we know an exact other point that lives on the brown tangent line? No, we only have points that live on the graph of x squared. We don't have another point that lives on the tangent line. So that was the problem. People wanted to know, what's the slope of the tangent line? What's the instantaneous rate of change? And the algebra that existed was insufficient to answer that question. So along came Newton, who was interested in finding the instantaneous rate of change, which helped them describe how planets moved in their orbits. And then Leibniz in Germany, at roughly the same time, he wasn't interested in instantaneous rate of change. He was interested in slope of the tangent line. But they're the exact same thing, instantaneous rate of change and slope of tangent line. So those two guys get credit for discovering this new branch of mathematics that allows us to find that. And it's called calculus, except they didn't call it calculus back in the day. Newton called his method the method of fluxions. What's the key word there for fluxions? Fluctuate, right? Because things change. Right? If things change, they fluctuate. So he called his the method of fluxions. And Leibniz called his the method of infinitesimals. What's an infinitesimal? Something that's really, really infinitely small. Right. Small. They were called the ghosts of departed quantities. They were that small. Ooh, poetic. Okay? So we're going to kind of get into how they circumvented the problem with only having one point. But it goes back to lines. We want to find the slope of the tangent line. Okay, so let's do one more problem and we'll call it a day, huh? I'm worn out. Find the slope of the line given by the general form equation. 5x minus 3y equals 2 at x equals 3. All right, so it says first find the slope of the line. So this is called general form. General form for a line is of the form ax plus by equals c, where a, b, and c are elements of the integers, right? Which means we don't have fractions. So if we want to extract the slope from the equation of a line, what form is preferred? The mx plus b form, because if you can get it in that form, the coefficient of x, the linear coefficient, is your slope. What do we call that form? It's the slope-intercept form. Yeah, pretty good name for something that gives you the slope and the y-intercept. So let's go ahead and algebraically do that. We're essentially going to solve for y. That's what we're interested in doing. Solve for y. Why? So we can get it in slope-intercept form. Thanks for asking. So negative 3y equals negative 5x plus 2. Bring the 5x across. Divide through by negative 3, and you get negative 5 negative thirds x minus 2 over 3. And if you simplify, of course, you get y equals 5 thirds, x minus 2 thirds. So the slope is 5 thirds. That's the average rate of change of that function between any 2 points anywhere on the function. It changes at a constant rate. Now it says find the functions of the line's instantaneous rate of change at x equals 50. So the instantaneous rate of change, which I'll abbreviate like that, at x equals 50 is, or negative 50 I said, yeah, negative 50, is what? 5 thirds. Very good. Because we just said something very unique about a line. The average rate of change between any 2 points is the exact same as the instantaneous rate of change at any single point, because lines are kind of boring in that respect, but they also can prove useful for that very same reason, okay? But not all things follow a linear growth rate, okay? So that's why we have to develop things for things that actually have curve, that change at variable rates. What would happen, okay, then find the line's average rate of change on the interval from negative 50 to 3. So what would be the average rate of change between x equals negative 50 and 3? 5 thirds, right? If you drive from here to San Antonio, and let's say You're on cruise control going 65 miles per hour. Very safe speed. You're in the right lane, okay? 65 miles per hour. That means you pull out of your driveway at 65, right? You're going 65 the whole time. Okay, just imagine that. You're on cruise control. What is your speed at any given moment? As you're driving, you look down, what's your speedometer say? 65. Okay, a couple seconds later, you look down, what's your speedometer still say? 65. Good. If you calculated your average velocity over the entire trip, what would it be? 65. That's linear, right? Your average velocity, which measures your rate of change of position, is the same as your instantaneous velocity at any given point. The graph of your position would look like a straight line, okay? Your graph of your position would look like a straight line. Here is miles from home. Here's time in hours, and it would look like that, right? And what would the slope of the line be? It'd be 60 miles per hour, okay? So it's a rate of change. Very boring, though. What would happen to the slopes at a particular x value if the given line were vertically shifted up or down? What if we took that line and moved it up or down? What would happen to the slope? Stays the same. What do we call those lines? Parallel. And parallel lines have the same slope. So it doesn't really matter what the starting value is, if you started at home or you started at your neighbor's house. That's just the y-intercept. The y-intercept is your starting position. If you're still driving at 60 miles per hour the whole time, it doesn't affect your rate of change, okay? So slope is no longer just rise over run. Slope is rate of change, yes? Between 2 points, it's called average rate of change, and it's the slope of the what line? Yeah, in general, it's the slope of a secant line, right? We saw that over here. Now, if you draw a secant line, if you connect these two dots on the line, you get the line itself. So a line is its own secant line. So let's just summarize this right here. The average rate of change is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And we call that the what? The D quotient, the difference quotient. And it's equal to the slope of the what line? Secant line. Secant line. It connects 2 points. Slope of the secant line. Whereas the instantaneous rate of change, which is going to require calculus, because the algebra fails, for non-lines, okay, it's going to be known as y prime, or dy dx. You don't have to know what that is just yet. But that's what we call that. We call that y prime, or dy dx. It's going to be known as the derivative. That's what it's going to become to known as, the derivative. And it's the slope of the what line? Tangent line. So we haven't gotten into how it was done or what that notation means, but it's going to be called the derivative, and it's going to be a function that allows you to find the instantaneous rate of change. So like in physics, you memorize your kinematics. You have position, velocity, and acceleration. It turns out that if you take the derivative of position, you get the instantaneous velocity equation. Okay, it shows you how fast the position is changing at that instant for that value of t. And then if you take the derivative, the rate of change of velocity is called acceleration. And you can actually then plug a single value of time into that acceleration equation and find how fast or what the acceleration is at the moment, which tells you how fast the velocity is changing. So those three equations actually came from calculus, from the derivative, okay? It turns out that the instantaneous rate of change of position is velocity, and the instantaneous rate of change of velocity is acceleration, okay? So that's what we're after for any function. How can we come up with that single function like velocity that we could just plug into at that moment and figure out what the rate of change is at that moment? Okay, we'll stop right there. Any questions? We got like 10 minutes left to chill or practice karaoke.